let's have a look at moments, beams, and bending moments. So these points or topics are going to be dealing mainly with the topic of beams, but it is that all these different topics do blend in together with each other. Okay, so let's consider, you might have come across the equation of torque is equal to force times distance. Okay, so this is where you might torque, you might often have heard in terms of the a piece of equipment like a torque wrench, and essentially torque has got to do with how much force you're able to apply at a certain distance. So the larger your distance is that your force is applied to a lever, the larger the torque is. So for example, if you consider a normal type of a spanner type of configuration, such as this. Okay, so if this if some force is applied over there, let's say that is 10 newtons, then to turn the nut that you want to turn with the spanner over here, there'll be quite a bit of torque involved, because there's going to be some arm distance over there that might be, let's say, 200 millimeters. But if you're having difficulty, 10 newtons is the only amount of force you're able to have. Maybe you're not a very strong person, and that's the amount of force that you're able to apply to untie a nut. If you want to increase the torque, then what you can do is you can maybe put like a pipe over this handle. Okay, so this is like a cross-sectional point of view. Take a pipe, which would be much longer, and then that might be, let's say, give you an additional 300 millimeters. Now applying 10 newtons over there is going to make it much more, or will increase the torque, and that will cause that you would probably be able to then loosen that specific nut. Okay, so moments is equal to force times distance. So it's very similar to your torque equation. Okay, and this is the important equation that we're going to be dealing with throughout this specific video. And you'll actually see that these moments, which is force times your distance or force times your arm distance, are actually equations that are used in different applications, as we'll see later on. And a specific application would be the weight and balancing of a specific aircraft. Okay, so if you look at this, how does it all fit together? Well, let's say, for example, you had a seesaw. You went to the playground and there's a seesaw. Okay, and this specific seesaw is 5 meters each side. Okay, so it's 5 meters there and 5 meters there. And you've got a little kid that's sitting over here, possibly, and they weigh, let's say, 40 kgs. Okay, so if another kid had to sit on this side and they weighed 40 kgs, that would cause this seesaw to be balanced. But now you get a person, adult maybe, and they 100 kgs, and for this seesaw to balance, they would have to stand over here. Okay, because they are 100 kgs. Okay, so how far away from this pivot point would they have to stand? We'll call that X. Okay, so essentially, when you do these type of applications and scenarios, there's an equation we use which is clockwise moments is equal to anti-clockwise moments. Very important equation that we will be using quite often. Okay, so if you had to place a pen at that pivot point over there, okay, and you had to say, okay, let's look at all forces acting in a clockwise direction. So obviously this 40 kg over here is going to be part of a force going down over there, and this 100 kg is going to be part of a force acting down over there. Okay, so if you place your pen over there and you go in a clockwise direction, this 100 kg is going with the clockwise direction. Okay, so we're going to take that into account. Okay, so therefore 100 kg times by 9.81, because we need to get a force. It's force equal to weight times acceleration, or weight times gravity. Okay, multiply by distance x, which is our distance in this equation, must be equal to, and now we look at anti-clockwise direction. So if we had to place our pen at a pivot point, we had to go in an anti-clockwise direction, we will ignore this 100 kg because it's going against the anti-clockwise direction. But this 40 kg is going with the direction of anti-clockwise. So therefore, we'll take that 40 kg into account. Okay, so that is 40 times 9.81 to get a force, multiplied by 5 meters. Okay, and therefore, when you calculate x over there, x would be equal to 2 meters. Okay, so that would indicate that this 100 kg person would have to stand 200 meters, at least 2 meters away, and this 40 kg person would have to sit 5 meters away, and the seesaw would be balanced. Okay, so basically the moments on either side of this pivot point need to be the same. So even though you've got a bigger weight over there, you are able to then allow that to counteract by having different moments in different distances. Okay, so let's do an experiment and see what how we can do this with using things that we are available with the seesaw type of scenario and washers for weights. I've got a setup over here with a dowel stick that's got 2 washers on either side, so it's perfectly balanced. You'll see in the middle over there is a black line, and that line indicates the center of this dowel stick. The dowel stick is exactly 270 millimeters in length, and these other markings along the way are in segments of 20 millimeters each. Okay, so each washer is 5 grams in weight, and we are able to then therefore see how far they are placed from each other and where the center or the balancing point would exactly be. Let's look at the first scenario. So I've placed on the left hand side 2 washers, and on the right hand side there's 1 washer. So at the moment it's wanting to tip to the left hand side. So where would I have to place this dowel stick, at least on this pivot point, to make it balance? Well, if I move it across a little bit over there, 20 millimeters, it's still wanting to tilt towards the left. The center pivot point is away from this specific washer 1, 2, 3, 4 segments of 20 millimeters, so it's away 80 millimeters. Okay, let's draw this scenario on a piece of paper. So 270 millimeters was the actual size of that dowel stick, yet only 240 millimeters was used. In other words, there were parts of the dowel stick on the sides where there wasn't any weights on, so we're going to ignore those sides for now. Okay, so I'm going to be using a scale of 2 to 1, which means that the distance of this specific beam or dowel stick is going to be 120 millimeters. As such. and 80 in an experiment we had 80 millimeters, which was up to the pivot point. So using a scale of 2 to 1, that means it's going to be at 40 millimeters that our pivot point is going to be, and we're going to present it like that. Okay, we had 10 newtons at or at least 10 grams, that was over there, and we had over here 5 grams. Okay, so this was 160 millimeters and this was 80 millimeters. Okay, so now we're going to use the formula that clockwise moments is equal to anti-clockwise moments. Alright, so we're going to be looking at the pivot point, and we're going to be looking at all the forces acting in the clockwise direction. So this 5 grams over there was acting in a clockwise direction. Okay, so that would mean that we've got 5 grams multiplied by 9.81. Okay, that gives us our force. Multiply that by 160 millimeters. Right, and that must be equal to our anti-clockwise moments. So the anti-clockwise moments is our 10 grams over there, so that's 10 multiplied by 9.81 multiplied by 80 millimeters. Okay, so 5 times 9.81 plus 160 is equal to 7848. 10 times 9.81 times 80 is equal to 7848. Okay, so therefore those moments on either side, the clockwise moments and the anti-clockwise moments, are equal to each other. And that's the reason why it balanced at that specific point over there. Okay, let's look at this specific scenario. So I've got 3 washers that's on the left hand side, and they spaced 40 millimeters away from each other. And then I've got 3 washers on the right hand side, right at the end. And let's see where this will balance. Okay, so if I place it over there, it seems to be balancing on a pivot point. Okay, so that indicates to us that we've got 2 segments over here of 20 millimeters, so it's 40 millimeters in between over there. We've got another two segments of 20 millimeters, which is 40 millimeters between those 2 washers, and there's 1, 2, 3 segments of 20 millimeters up to the pivot point, which makes us 60 millimeters away. And then if we look from these 3 washers coming across to the pivot point, we will see that there is 1, 2, 3, 4, 5 segments of 20 millimeters, so that's about 100 millimeters distance. Okay, so let's look at the second scenario. So again, we've got a beam that is going to be drawn a scale of 1 to 2. Okay, so therefore it's 120 millimeters to represent a 240 millimeters in the experiment. Okay, and essentially what we had is we initially had at an end point of a force that was 5 grams. Okay, 40 millimeters away from that was another force that was 5 grams. Okay, then 40 millimeters from there we had another force. Okay, so that's 40 millimeters, which was 5 grams. Okay, and then we had 60 millimeters, which is a scale of 2 to 1 would be 30 millimeters. Okay, and that was where our pivot point was. Right, and then from the pivot point, okay, so that was 60 millimeters. From pivot point to the end over here, we had 100 millimeters, and we had 15 grams weight over there. Right, so again we're going to say clockwise moments is equal to anti-clockwise moments. Alright, so we're going to place our pin over here and use it as a pivot point. So going in a clockwise direction, it seems to be this 15 grams is going in a clockwise direction. Okay, so it's 15 grams multiplied by 9.81 multiplied by 100 millimeters. Okay, and that's going to be equal to, well, we don't see any other clockwise moments over there. All these forces over here are going anti-clockwise direction. Okay, so we can look at the anti-clockwise direction moments. Okay, so that is going to be first 5 grams. Okay, so we're going to start with this one over here, 5 grams multiplied by 9.81. And we multiply it by the distance, so that's 60 plus 40, which is 100, plus another 40 is 140. Okay, plus another 5 grams multiplied by 9.81. Okay, multiply that by that distance, arm length over there, which is equal to 60 plus 40, which is 100. Okay, plus our next force is another 5 grams multiplied by 9.81, and the distance from there to the pivot point is 60 millimeters. Okay, so now that we've got this, if we calculate 15 multiplied by 9.81 multiplied by 100, we get 14715. Okay, let's see if that is equal on the right hand side as well for the anti-clockwise moments. Okay, so 5 times 9.81 times 140 is equal to 6867, plus 5 times 9.81 multiplied by 100 is equal to 4905. Okay, then 5 times 9.81 multiplied by 60 is equal to 2943. Okay, and if we add those values together over there, we get 14715. So that shows that our clockwise moments is equal to our anti-clockwise moments. Okay, so something just to be aware of that we need to take into account. So what is the force acting on this specific pivot point? It's a single pivot point we've got over there. So whenever you've got a single pivot point, then you're basically saying that upper forces is equal to downward forces. Okay, so therefore the force at the pivot point, and we'll call that, let's say, A. Okay, so force at A is equal to 5 times 9.81 plus 5 times 9.81 plus 5 times 9.81 plus 15 times 9.81. Okay, and if we calculate that, we will get an answer of 294.3 newtons. Right. Now, that is actually incorrect, because this is taken into account, it's 5 kilograms. Remember, force is equal to mass times gravity, and mass needs to be in kilograms. Okay, so this is out by a factor of 1,000. Okay, so in reality, it would be equal to 0.2943 newtons. Okay, so the first thing we need to also take into account is, even though in this specific example or scenario I use grams, always make sure that your weights are in kilograms. Okay, and also these must be forces that you need to show over there. So convert, if you've got a weight over there, convert that into a force in Newton specifically. Okay, and then also keep in mind that your upward forces equal to downward forces. And then also I've got over here distances in millimeters. Just be careful, these distances always need to be in meters. So if you remember, force is equal to mass times gravity. Okay, so force is in newtons, mass needs to be in kilograms, and gravity is in meters per second squared. Okay, and then also when we've got our moments, that's equal to our force multiplied by our distance. Okay, so our moments will be in Newton meters, our force must be in newtons, okay, and our distance must always be in meters. So just make sure that when you do your calculations, all the values are in those basic units, and then that will prevent you from making any specific errors. Let's have a look at this example. So what I've done is I've already drawn out the beam. I've got 2 pivot points over there, and okay, so over there and over there. 30 meters away is 50 newtons acting downwards. 20 meters away from that point is another force of 5 newtons, and that is 30 meters from this specific pivot point. So essentially the distance from this pivot point to that pivot point is 80 meters. Okay, so what I'm going to do is I'm going to call this pivot point over there A. This force I'm going to call B. So B is equal to that. This force of 5 newtons I'm going to call C. And this pivot point I'm going to call D. And you'll see the reason why it's important to label these specific points. Okay, so what I've also done is at each of these points where there would be some other force acting on that specific beam, I've drawn down vertical lines with a ruler very accurately, and we will be using that very soon. But before we look at that, we need to calculate what is the forces at A and at D. Okay, so what we're going to do is we're going to therefore say take moments about A for D. Okay, and so we're going to be taking moments about this pivot point A. Okay, because now we've got, the thing is we in the past we had only had one pivot point, and so we were able to calculate clockwise moments equal to anti-clockwise moments. So we're going to be doing exactly the same thing, but because we've got two unknowns, it's essentially simultaneous equations we've got to do. Yet we don't have to do it as complex as that. There is an easier way to do it. The way that I'm going to be showing you now, there are other ways that you can go about to solve these type of problems. But with the way that I'm showing you, it is to make sure that there's some consistency in your calculations. It is making sure that you don't make errors, so we actually check our answers in some other way. And it's also to make sure that your solution is going to be always the same. If you do it other ways that might be out there, it might mean that your solution would appear differently, especially with the plotting of the graphs. And that could be at the first glance look like you are incorrect. Okay, so therefore I'm advising that you follow this approach to solve these problems. Okay, so if we're going to be looking at about point A over there, we're going to say, okay, clockwise moments is equal to anti-clockwise moments. Alright. Okay, so first we're going to be looking at, we've got 50 newtons over there. So our forces are newtons, so we don't need to multiply by 9.81. Okay, so we've got 15 newtons over there multiplied by 30 meters. Okay, then we've got another 5 newtons over there multiplied by 50. 30 plus 20 is 50. 50 meters over there. Okay, and that must be equal to our anti-clockwise moments. So again, if you put your pen on point A over there, and you go at all forces going in anti-clockwise direction, that would mean that D is the only one that will be doing it. So that will be, D is the distance of 30 plus 20 plus 30, that's 80 meters, multiplied by D. Okay, so let's calculate it. So that's 15 times 30 is equal to 450. Okay, 5 times 50 is equal to 250. Right, and that's equal to 80 D. Okay, so 450 plus 250 is 700. Okay, so therefore 700 is equal to 80 D. Okay, and that implies that D is equal to 8.75 newtons. Okay. Now that we've got D, we can actually write it in over here. So that's equal to 8.75. Okay. Now we've got D, we need to calculate what A is. Okay, so we're going to be doing the same approach. So we're going to be taking moments about D this time for A. Okay, so again, clockwise moments is equal to anti-clockwise moments. Right, so we're going to place our pen now on pivots D and start looking at clockwise moments. Well, at the moment, the only clockwise moments over here would be with force A. Okay, and A is again 80 meters away. So 80 times A. Okay, there's no other clockwise moments over there. That's equal to, now let's look at the anti-clockwise moments. That would be B and C. Okay, so that's equal to B, which is 50 newtons, multiplied by 50 meters, plus C, which is 5 newtons, multiplied by 30 meters. Okay, so therefore 80A is equal to 15 times 50 is equal to 750, and 5 times 30 is equal to 150. Okay, and so that would be equal to 900. Therefore A, if we say 900 divided by 80, is equal to 11.25 newtons. Always important to have your units after your values. Without units, you get it wrong. Okay, so we can actually then write in over here, A is equal to 11.25 newtons. Okay, now that we've done that, we need to draw a shear force diagram. Okay, so a shear force diagram is essentially plotting your different points of forces. And to do this, we're going to be again drawing a line to represent our beam. Okay, so I'm just going to write over here, shear force diagram. Okay, and if you look at these forces, 11.25, 15.5 and 8.75, if I want to use millimeters to plot that, or let's say 11 millimeters to plot 11.25 newtons, I'm able to do that on a sheet of paper. So there's no scaling required in a specific case, or at least in this example. Okay, so I'm going to be drawing again a straight line that's going to be completely perpendicular to my lines that's coming down from my original beam over there. So I'm replicating the beam over there, and A is 11.25 millimeters. Okay, so 11.25 millimeters would be roughly over there. Okay, so that is 11.25. Right, so we can draw a line over there for that 11.25. Okay, then we've got a force over here of 15 newtons going down. Okay, so we're going to be drawing a straight line across from A to B, because there's no other forces acting over there. It's only at B that there's another force acting, so we're going to be drawing a straight line over there, and at B 15 newtons is going downwards. Okay, so we are able to draw 15 millimeters down over here, which will be over there. Okay, so now if we say 11.25 minus 15, that will leave us at minus 3.75. Okay, so we can draw a straight line over there. Alright, now that we've done that, there's no forces between B and C, so we can draw a straight line across. At C, there's 5 newtons going downwards, so that would be 5 millimeters down from there. Okay, and that would be at minus 8.75. In between C and D, there's no forces acting over there, so it's a straight line going across. But at D, it's 8.75 going up. And if we did this correctly, you should have 8.75 going up over there. Okay, unless your lines were not exactly straight. Okay, and that goes back to 0. Got 0 over there. Okay, so that's our shear force diagram. Something else we just need to check before we continue, and we should have done this before we did the shear force diagram, is with these calculations over here, are they accurate? Okay, so remember, upward forces needs to be equal to downward forces. Okay, so let's just check. For upward forces, we've got 11.25 and we've got 8.75. Okay, is that equal to our downward forces, which is 15 plus 5. Okay, so 11.25 plus 8.75 is equal to 20. So therefore 20 is equal to 15 plus 5 is 20. So there's a 95% chance that we've done our calculations correctly. Okay, so always just have us check over here. Okay, so we're going to just have a check. Always have that check before you start doing the shear force diagrams. Okay, now that we've done the shear force diagram, we need to do a bending moment diagram. Okay, so a bending moment diagram follows the following sort of procedure. So first we need to calculate the bending moments at each specific point. Okay, so to do this, you need to actually take a sheet of paper and place it over your diagram and look at everything that is to the left of that piece of paper. Okay, so for example, I'm going to be looking at the bending moments. Okay, so this is now bending moments. Okay, so the bending moments for A. Okay, so we place a piece of paper over our beam drawing over there, and we look at everything that's to the left of the sheet of paper. Okay, so in this case we told it that A is equal to 11.25, but the piece of paper is actually covering it at that specific point. We actually have to ignore it. Okay, so it's everything to the left of it, any forces to the left of it. Okay, so The bending moments at A is equal to 0 Newton meters. Okay. Now with what we're going to be doing is we're going to be considering all upward forces to be positive and all downward forces to be negative. Okay, so that's going to be our sign convention that we will always use. Okay, let's look at the bending moments at B. So we place a sheet of paper over B over there. We look to the left over there. Okay, so A is the only force that we can see over there. So A is equal to 11.25, and that is 30 meters away, multiplied by 30. Okay, and that is equal to 337.5 Newton meters. Okay, now we're going to go to the next point, bending moment for C. Okay, so we place a sheet of paper over at point C, and again we look at all the forces acting to the left hand side. We're going to be ignoring C at a specific point there. Okay, so that is equal to A, which is going to be upward force, so that's a positive force, so that is 11.25. A is 50 meters away. Okay, so multiply by 50. Then we've got B acting downwards, so that's a negative force that we're going to be looking at. So that's minus 15 newtons multiplied by, and that is 20 meters away from C. Okay, and once we've done that, that is equal to 262.5 Newton meters. Okay, now we're going to go to point D, which is that last pivot point over there. And now we're going to be looking at all the forces acting to the left of it. Okay, so bending moments for point D is equal to, okay, so we've got A, which is 11.25 newtons, which is 80 meters away. Okay, we've got B acting downwards, so we're subtracting that. That's 15 newtons over there, multiplied by 30 plus 20 is 50. We've got C acting downwards, so that's another negative sign, which is 5 newtons, multiplied by 30 meters away. And if we do that calculation over there, we will get a value of 0 Newton meters. Okay. Alright, so now that we've done this, we are going to need to plot it. Okay, so this is where it becomes a little bit tricky. We're going to have to use a scale because we've got forces of 337 newtons over here. Okay, so I want to make it that that would be estimated to be 33 millimeters. Okay, so I'm going to use a scale of 10 to 1. Okay, so bending moment diagram. Okay, so I'm going to say over there, scale is going to be 10 to 1. Okay. Alright, so what we're going to do is we're going to be drawing a beam across again to represent, well, a line going across to represent our beam. Okay, as such. Okay, so the beam moment at A is equal to 0 Newton meters. So that's at 0 over there. Okay, so we can place a 0 over there. Then we've got beam moment at B, which is 337.5 Newton meter. Okay, so I'm going to draw measure over here. That's going to be 33.7 millimeters, which will be over there. Okay, so that would be 33 or 337.5 Newton meters. Okay, then bend moment at C is 262.5 Newton meters. Okay, so from our zero line at our beam, we're going to measure 262. In this case, it would be 26.2 millimeters. Okay, so that is 26 or 262.5 Newton meters. And then a bend moment at D is at 0, so 0 Newton meters. Okay, and then all that we do is we join the dots. Okay, so from this 0, it goes to 337.5. And from 337.5, it goes to 262.5. Okay, so we've got that dot over there. And then from there, it goes to 0. Right. And so that is our bending moment diagram for this specific problem. Right, so what we've seen up to now is, this is a very basic type of example, but the procedures we're going to be following for even more complex problems are going to follow this exactly same procedure. And if you follow again the same procedure, the chances of having any errors will be minimized. Let's look at another example. Because I've drawn again the beam over here, and I've drawn it to scale. You can check it with a ruler. I've got 2 meters over there, which is 20 millimeters that I've drawn with the ruler. 3 meters over there, which is another 30 millimeters. Another 3 meters over there, which is also another 30 millimeters, and another 2 meters, which is another 20 millimeters, as shown over there. Okay, so this is something very similar to what you've seen, with a few additions. And so you also see that I've projected all my lines where there's forces and stuff. Some of them you might not be seeing forces at the moment. I'll explain to you where they appear and why they're there. The difference we've got over here, well, let's just have a look at what it consists of. So we've got our beam, which got support A and D, so 2 pivot points A and D over there. We've got our force B over there, which is 20 kilonewtons downwards. We've got a force of C, which is 14 kilonewtons downwards, and we've got the force E, which is 30 kilonewtons downwards over there. Okay, so essentially there's a bit of a difference over here in terms of something you haven't seen before, and that's these squiggly lines that I've drawn over here. Okay, so those squiggly lines represent a distributed force. So what would be a common scenario or application where you would have this distributed force? So let's say you've got some beam, and on top of this beam you want to have a concrete slab that's going to be 2 meters in length. Okay, so that slab will be a distributed force across that 2 meters. And for this specific scenario, we are told that for this distributed force, we've got 20 kilonewtons per meter. Okay, so 20 kilonewtons is acting downwards for every meter of that slab. So because we've got 2 meters of slab over there, we've got to multiply this 20 by 2. Okay, so that's equal to 40 kilonewtons in the center of this distributed load. And I'm going to call that A1, because that's just between A and B over there. Okay, if you look at this distributed load over here, it's again also 20 kilonewtons per meter. It could have been different, but in this scenario it is 20 kilonewtons per meter. And again, we've got it right in the center over here. We're going to, of this distributed load, we're going to have our actual force over there. And we're going to call that C1. Okay, so if it's 20 kilonewtons per meter, and this is 3 meters in length, that means that's going to be 60 kilonewtons. Okay, and now you can sort of see the reason I've plotted these lines down over here to take into account where these forces are that are in the center of these distributed loads. Okay, so now that we've got the problem over there, we've expanded it, put in all our values and stuff. The first thing we're going to have to probably find is what A and D is. Okay, so to find A and D, okay, so we're going to take moments about A for D. Okay, so therefore our anti-clockwise moments must be equal to our clockwise moments. Okay, so about A, what is going to be anti-clockwise moments about A? Well, if we go in an anti-clockwise direction, these are all forces all going against our anti-clockwise direction. It's only D that will be. Okay, and D is what distance away? It's 3 plus 3, which is 6, plus 2, which is 8. It's 8 meters away. Okay, so therefore D times 8 is equal to, okay, and there's no other anti-clockwise moments that we can see. Okay, so now we're looking at the clockwise moments. Okay, so that's going to be, we can see that we've got over here our 40 kilonewtons for A1. Okay, and that's 1 meter away. Okay, so that is 40 multiplied by 1 plus, we've got B over here, which is 20 kilonewtons, and that's 2 meters away. Okay, then we've got C over here, which is 14 kilonewtons, and C is 3 plus 2, which is 5 meters away. Okay, and then we're going to be looking down here. C1 is 60 kilonewtons. Okay, so we're going to say plus 60 kilonewtons. How far is C1 from A1? Well, keep in mind that C1 is in the middle of between C and D. Okay, and that is 3 meters. So that's half of that is 1.5 meters. Okay, so it's 2 plus 3, which is 5, plus 1.5 meters, which is 6.5. So we multiply by 6.5. Okay, then we're looking at further. We see how there's this distributed load over here, which is characterized by C1. Okay, so that is plus 6. Sorry, no, we've done that now. We're looking at now E. Okay, so E, which is 30 kilonewtons, so that is plus 30 kilonewtons. Okay, and that's the distance of 2 plus 3 plus 3 plus 2. That's 10 meters away, so multiply by 10. Okay, right, and so if we do that calculation and we divide by 8 to find D, we find that therefore D is equal to 105 kilonewtons. Okay, you will realize that all these values, forces that I've taken into account, I might have not written times 10 to the 3 over there, but I've kept them in context so that I can get a correct answer in kilonewtons as shown over there. Okay, so now we're going to take moments about D for A. Okay, so again we've got our clockwise moments is equal to our anti-clockwise moments. Right, so if we're going to be taking it about D, and we look at what forces are going in the clockwise direction, well, we've got A over here, okay, and that is what distance away? 3 plus 3 is 6, plus another 2 is 8 meters away. Okay, so therefore A multiplied by 8. So one clockwise direction moment we see over there. But if we keep on looking over here, if we've got our pivot point over here at D, and we look at all the forces acting in a clockwise direction, you'll see that E is also going in a clockwise direction around D. Okay, so we've got to take that into account. Because therefore, plus E is 30 kilonewtons. And how far is E away from D? It's 2 meters. Okay, so there's no other further clockwise moments we can see over there. Let's now start looking at the anti-clockwise moments around D. Okay, so that's equal to, okay, so first we've got a 60 kilonewtons, which is for the distributed load. So that is 60, and that is 1.5 meters away. Okay. Right. Then, if we look on further, we've got C over there. Okay, so plus 14 kilonewtons, and that is 3 meters away. Right. What other forces do we have that goes in the anti-clockwise direction? We've got B. Okay, so we've got plus B, which is 20 kilonewtons, and that is 3 plus 3 meters away, so that's 6 meters away. Okay, and then we've got this 40 kilonewton distributed load. So plus 40, multiply how far is it away from D? Well, it's 3 plus 3, which is 6, plus 1 meter, which is half of that 2 meter over there. Okay, so that's 7 meters away. Right, so we do the calculation, we subtract this over here, and we make A the subject of the formula, and we find that A is equal to 59 kilonewtons. Okay, let's check to see if our calculations are correct. Remember, upward forces must be equal to downward forces. Okay, so D over here, we're going to just indicate that's equal to 105 kilonewtons, and A we calculated to be 59 kilonewtons. It's always a good thing to put these values into your drawing so that you can see everything in front of you and you don't have to look for it. Okay, upward forces. Okay, so we've got 59 plus 105 kilonewtons. Okay, no other upward forces seen over there. Let's look at the downward forces. Well, we've got a 40 over there. We've got a 20 over there. We've got a 14 over there. We've got a 60 over there. And we've got a 30 over there. Okay. Right. So therefore, 164 kilonewtons is equal to 164 kilonewtons. So there's a 95% chance that we are correct over there with our calculations. Okay, now that we've done that, the next thing we've got to do is we've got to draw the shear force diagram. Okay, so again, I'm going to be drawing our beam over here. And that's all a line going across to represent our beam. And it's always good to try and make these drawings as accurate as possible, so that you can verify also your answers. Okay, so we've got 59 going over there. So I'm going to be using a scale of 1 to 2. Of a half, so everything I'm going to half over there. Okay, so if we've got 59, that's for A, and we half that, that's 29.5. So I'm going to be measuring 29.5 over here. Okay, and I'm going to indicate over there the 59 kilonewtons. Okay, Okay, so now that we've done that, if we look at B, we've got over there at B 20 kilonewtons, but we can't neglect the 40 kilonewtons that is between A and B for that distributed load. Okay, so essentially what we've got to do is we've got 40 kilonewtons coming down. Okay, so for us to do this, we have to measure the 40 kilonewtons down from the 59, and we're going to be doing it on that specific line. Okay, so if you look over here, again we're looking at a scale of 1 to 2, so 40 kilonewtons going down would be a measurement of 20. Okay, so measuring 20 down over there from that point, which is roughly over there, and I'm going to project that 20 across to where point B is. Okay, so that would be where the force B is. So that is the 59 minus 40 newtons gave us our mark over there. Well, it was 20 millimeters downwards, and I projected across to over here where the distributed load ended, which is over there. Okay, so over there I'm going to be making my dot, and that is going to be at 19. 59 minus 40 is equal to 19. Okay, so that 40 is from A1 over there. Okay, right, so now that we've done that, we see at B there's 20 kilonewtons acting downwards. Okay, so that 20 kilonewtons we've got to now project downwards as well. Okay, and keep in mind that would be from there, and we'll be just going 1 millimeter below. So basically or half a millimeter below the line over there. Okay, so keep in mind it's 19 minus 20. Okay, and that's a 10 millimeter. 20 would be 10 millimeters that we're projecting downwards, and that's where we get this over there. Okay, and that's at minus 1. Okay, so we can actually start just drawing our lines. So if we went from 0 to 59, you can join those dots over there. And from 59 we went across to 19. So our distributed loads are indicated with a diagonal line. So joining those two lines together over there. Okay, and then from 19 it went to minus 1. Okay, so we can draw that line down to there. Right, now that we've done that, from B we're going to C, and at C that's shown to us that is another 14 kilonewtons going downwards. Okay, so we can draw a straight line across. Because it's not a distributed load, we don't have to worry about diagonal lines. Okay, so we draw that line across over there. Alright, so at C, that's 14 kilonewtons downwards, so that's going to be equivalent to 7 millimeters. Okay, 6, 7 over there. Okay, so that's going to be representing minus 15, because minus 1 minus 14 is equal to minus 15. Okay, and we can draw our line over there between the two dots. Right, now we've got this distributed load over here. Okay, so that is equal to 60 kilonewtons. Now 60 kilonewtons is going to be represented by 30 millimeters. Okay, so I'm going to be projecting 30 millimeters from that 15 point over there, which is going to be over there, and because it's a distributed load I'm going to project it across up to point D. Okay, so that's going to be over there. Right, and because it's a distributed load, okay, so I'm going to write over there it's minus 75, because minus 15 minus 60 is equal to minus 75. And I'm going to join those two dots together. Right. Now at point D, we've got 105 newtons acting upwards. Okay, so 105 divided by 2 is equal to 52.5. So I'm going to be drawing 52.5 from there. Okay, so 52.5 will give us a point over there. Right. So minus 75, right, plus 105 is going to give us an answer of 30. Okay, so I can draw a line between those two dots. Okay, between D and E, there's no forces, so I can just draw a line going across from E. Make sure your lines are perpendicular to each other so that you don't make any errors. And then E is 30 kilonewtons downwards, which is equal to 15 millimeters. And if we take a measurement over there, you'll see that is exactly 15 millimeters going downwards over there. Okay, so that goes back to 0. Alright, so we've done our shear force diagram. The next thing we've got to look at is now to draw the bending moment diagram. Okay, so I'm just highlighting over here what are the main points we've got to look at. Okay, so now the next thing we've got to do is we've got to draw the bending moment diagram. Okay, so again, remember, as I said, we're going to place a piece of paper over it, and we're going to be over our beam, and we're going to be looking at all the forces to the left of it. Okay, so keep in mind that upward forces is going to be positive, and downward forces is going to be negative. Okay, so we're going to be looking at all the forces to the left. So bending moment of A. Okay, so if we place a sheet of paper over A over there, and you look to the left of it, there's no forces over there, so therefore bending moment of A is equal to 0 kilonewton meter. Okay, let's look at the bending moment for B. Okay, so we place a sheet of paper over B over there, and we look to the left of it. Okay, so over there we've got A, which is 59, and that is 2 meters away from B. Okay, but we've got A1, the distributed load, it's going downwards, so we've got to subtract that. So that's minus, we've got 40 kilonewtons. And how far is it away from B? Well, it is 1 meter away. Okay, we do that calculation, and that's equal to 78 kilonewton meter. Okay, bending moments for C. Alright, so go across, and we're going to be looking at C over there. Okay, so looking to the left over there, we've got A. Okay, so that's A, which is 59, multiplied, what's the distance from C to A? Well, that's 3 plus 2 meters, that's 5 meters. We've got the distributed load at A1 going downwards, so that's minus 40, and that's a distance of 3 plus 1, that's 4 meters away. Okay, and then we've got the load at B, so that's minus 20 multiplied by, and it's a distance of 3 meters away from C. Okay, and that results into 75 kilonewton meter. Okay, I'm going to sort of write on a new piece of paper over here just because I'm running out of space on the screen. Alright, so that was bending moment C. Let's look at the bending moment for D. Okay, so we're looking again, all the forces to the left of it. So A is 59 kilonewtons, multiply that by what distance is A from D? So that's 3 plus 3, which is 6, plus 2, which is 8. Okay, then we've got A1 going downwards over there, so we've got to subtract that 40 kilonewtons over there, and we've got to look at the distance it is away from D. So that's 3 plus 3, which is 6, plus a 1 meter, which is in the middle of that 2 meters over there, so that's 7 meters. So multiplied by 7. Okay, now we've got a 20 kilonewtons that's at B that we've got to subtract over there. So that's minus 20 multiplied by B's, what's the distance from B to D? Well, that is 3 plus 3, which is 6 meters. Okay. Right, then we've got the 14 kilonewtons for C. So that is minus 14 kilonewtons multiplied by distance from C to D is 3 meters. Then we've got C1, which is 60 kilonewtons. Okay, so that is 60 kilonewtons. The distance from C1 to D is 1.5 meters. It's half of 3 meters over there. Okay. We do this calculation and we find that's equal to negative 60 kilonewton meter. Okay. Then we've got to look at the bending moments for E. Okay. Alright, so let's have a look. That's equal to 59 multiplied by distance away from E is 10 meters. Okay, then we've got A1 over there, so it's minus 40 multiplied by the distance from E to A1 is 9 meters. Then we see, okay, the next one is B, which is 20 kilonewtons, so it's minus 20 multiplied by a distance of 3 plus 3 plus 2 is 8 meters. Okay. Then we go across and we see the next one is C. So minus 14 kilonewtons over there. The distance from C to E is 5 meters. Okay. Then we've got C1 that we need to subtract over there. Okay, so that is 60 kilonewtons, and that's a distance of 3.5 meters away. Okay, then we've got D. D's force acting upwards, so that's plus a positive force, not a negative force. That's 105 kilonewtons, and that's a distance of 2 meters away. Alright, now we calculate that. Okay, and we will get an answer of 0 kilonewton meter. This step over here for calculating the bending moments for E, you might say, oh, why should I even do it? It's always going to be 0 kilonewtons. Be careful though, it's not always the case. There are some scenarios that this might not be the case, so it's always good just to do the calculation every time. Alright, so now that we've looked at the bending moments and we've done these calculations, we've got to take 2 points into account. So essentially we've got these points A1 and C1. Okay, so, and because distributed loads with bending moments, it's not a linear line as we've got with our shear diagram over here. Okay, so with our shear force diagram, okay, I can actually put over here shear force diagram. Okay. We can't always, when it comes to bending moments, it's not a straight line in a linear fashion as that. It's a curve. So it's always a good thing to have another point over there. So we need to look at the bending moments of A1. Again, we're going to be placing a piece of paper over A1, and then we'll be looking at everything to the left of it. Okay, so bending moments of A1, that's equal to 59. Okay, because we've got A over there acting in the upward position, and that is multiplied by a distance of 1 meter. Okay, but we've got a distributed load over here. Even though we've got A1 over here that represents a full distributed load, when we cover that up, we're not taking that into account. We've got over here a small piece of distributed load that we need to take into account. Okay, so the distributed load is 20 kilonewtons, and obviously it's acting downwards, so we've got a negative value over there. Okay, so this is 20 kilonewtons acting downwards. Okay, and it's 20 kilonewtons per meter. And so that distance we've got over there between A1 and A is 1 meter. So we multiply it by 1 meter. Okay. Now, if we cover it up over there, we've got to look at the position of it between A1 and A, which is going to be, from A1, it's going to be half a meter away. Okay, so we multiply that by a half. Okay, so now that we've done that and we do a calculation, that's equal to 49 kilonewton meter. Okay, let's have a look at the bending moment of C1. Okay, so now we're going to be moving across to C1. Place a sheet of paper over there. Okay, so we've got A, which is 59 kilonewtons. Distance from A to C1 is 2 plus 3 is 5, plus 1.5 meters is 6.5 meters. Okay. Then we've got A1 over there. So we've got to minus 40 kilonewtons. Now, what's the distance from A1 to C1? Well, that would be 1 meter over here, plus 3 meter over here is 4 meters, plus 1.5 meters over there. So it is 5.5 meters. Okay. Then we're going to be going across. We've got B over there acting downwards. Okay, so that's minus 20 multiplied distance from B to C1 is 3 meters plus 1.5 meters, which is 4.5 meters. Okay. Then we come across, we've got C over there, so we're minus 14 multiplied by distance from C to C1 is 1.5 meters. Okay, and then we've got this distributed load over here that we've got to take into account as well. Okay, so again, the distributed load is 20 kilonewtons per meter. Okay, so if we're covering up at C1 over there, okay, so that is 20 kilonewtons per meter multiplied by, what's the distance that we've got for that piece of distributed load between C and C1? Well, that would be half of the 3 meters. That would be 1.5 meters. So multiplied by 1.5 meters. Okay, and then we've got to look at the distance it is away from there. Okay, so this 1.5 meters is only taken into account the total distribution from C to C1. We've got to look at that load will be obviously in the middle of C and C1 over there. Okay, so that's going to be the middle of 1.5. Okay, so we need to multiply that by 1.5 divided by 2. Alright, so if we do this calculation, we get a value of 30 kilonewton meter. Okay. Now that we've calculated this, we can start drawing our bending moment diagram. Let's take that sheet of paper away over there, and I'm going to move this up over there. Okay, we don't need to really look at all the values at the top now. We've got all the values written down over here on the left hand side, and we are able to start plotting it. Okay, so the first thing we're going to be doing is we're going to be looking at the bending moments for A. Bending moments for A is 0. Okay, so before we do that, we're going to be just drawing our line across to represent our beam. Okay, I'm going to also just over here at the bottom, bending moment diagram, and I'm also going to indicate over there that the scale is 1 to 2. Okay, right, so let's have a look. So bending moment of A is 0, so that's over there. Right, bending moment at B, that is 78 kilonewton meter. Okay, so 78 divided by 2 is equal to 39 millimeters. So 39 millimeters I'm going to go up over here. Oops, that's the wrong point. Remember, B is this line over here. Okay, so 39 millimeters is over there. Now keep in mind that we did calculate what the bending moment for A1 is, and we found that to be 49 kilonewtons. So we can actually plot it over here in the second line over there as well. So 49 kilonewton meters divided by 2 is equal to 24.5. Okay, so 24.5 will be over there. Okay, so I'm going to write my values in over there. Okay, so this is 49. Okay, this point over here is going to be 78. Right. Now we're going across. Our next point is C. Okay, and C we've calculated to have a bending moment of 75 kilonewtons. So from the center line, or the 0 line, 75 millimeters or 75 kilonewton meters upwards, and that's going to be, if we half that, that's 37.5 millimeters. So that is over there. Right. Okay, so that is equal to the bending moment at C, which is 75 kilonewtons. Right. Now that we've done that, we're going to be looking at the next point, which is C1. And C1 we've calculated the bending moment, and that is equal to 30 kilonewton meter. Okay, so half of that is 15. Okay, so 15 millimeters up from there gives us a position over there. Okay, and I'm going to write over there that that is 30. Okay, now we go to the next point, which is D. Bending moment at D is equal to negative 60 kilonewtons. Okay, so negative 60 kilonewtons, half that is minus 30 millimeters. So we've got 30 millimeters going below the 0 line, while beam line over there. Okay, so that is equal to minus 60. And then we looked at the bending moments at E, which was 0 kilonewtons over there. Okay, and I'm just going to indicate 0 over here at A. Okay, so now it's again a situation of joining the dots. But we've got to be careful though. If you look at these points between 0 or between A and B, it's not a linear line, as I mentioned before, and that's the reason we got this A1 bending moment over there. Okay, so it's more of a curve that is formed over there. If you've got technical drawing tools that are allowing you to make a better curve over there, you could do so. So I'm going to use my do it by freehand as accurately as possible. So it's going to be in a direction as such. Okay, now between B and C, it's just normal lows, there's no distribution lows, and that can be a straight line. Okay, then we've got between C and D, which is this point over here. Again, if you look at it with a ruler, you can see that that's not a straight line over there. If you have to go through this point C1, it's again going to be a curved line over there. So we're going to be doing a similar type of thing. And I'm going to be doing it by freehand. Again, just as accurately as possible. As such. Okay, and now that we've done that between D and E, it's just normal forces, there's no distributed load, so we are able to draw a straight line between those 2 points over there. Alright, okay, so that is our bending moment diagram, as you can see over there. Now something that's very important, always draw your diagrams from the left. Okay, so if you have a bending moment diagram and there's some distributed loads involved and stuff, your diagram will always appear something in the fashion of something like this. Okay, and as you can see, we didn't come down necessarily, but we've got a curve going up and then coming down and then upwards again. So that's sort of a rule of thumb that you can use to try and make sure that you've got at least a correct diagram drawn. Right, then the next problem that you might be asked is what is the maximum bending moment? Okay, and where will it break? Okay, so if you look at this, these diagrams, right? So if you look at the shear force diagram, it's intersecting over here, going through the zero line at point B. But if you look at your bending moment diagram, you also see that the maximum bending moment is 78 kilonewton or kilonewton meter, which will be at point B. Okay, and that will indicate to us that that will be where the break will happen. Okay, so we can say that is then 78 kilonewton meter. Okay, and it's at B that it will break. Right. Okay, so having a look at this, essentially it's the same principles that you're going to follow. You can get so many different scenarios with your beams. You can have the distributed load going across a whole beam, and the same principles will occur. You'll look at the middle of each distribution load, act a force on it, and calculate what it would be. So if it's 20 kilonewtons per meter, look at the distance that it is over there and multiply it by 20. So you could have different forces. Make sure that always the forces are going perpendicular downwards or upwards. If you do get forces in an angle, you might have to calculate it to sort of correlate it to the upwards and downward forces. But other than that, the same principles are going to apply for all the shear force diagrams and all the bending moment diagrams that you will be doing. We're going to be having a look at struts and ties. Okay, so struts and ties are an expansion of beams. So at this stage, we've looked at beams on what I want to call a one-dimensional scale, in terms of it's just a beam going across and there's forces acting on it. Yet with struts and ties, it expands it in a y direction, as we will see very soon. Just a few things we need to just become familiar with and be able to sort of have an understanding of what struts and ties are. Okay, so if you've got a beam as such, and you've got some force acting away from it, so it's pulling on that beam, then that's known as a strut. Okay, if you've got a beam that has forces acting against it, so pushing towards each other, that's known as a tie. And generally you would find that this would be where a tie could be almost considered like a rope. So if you've got some structure and a rope is or if any of these beams that we're going to be looking at should be a rope, a tie would be then causing the rope to actually be loose. But if it was a strut, the rope would be then tight. Okay, so we will see more in terms of how the struts and ties work in this beam scenarios and examples. Another thing we just need to look at, it's probably more of just a revision, is that if you should have some force acting down on that specific point, and let's say the force is equal to 20 newtons, we can say that that angle is equal to 30 degrees. Okay, then that would mean that you're going to have horizontal components and vertical components. The horizontal components will be equal to F cos theta, or in this case that would be equal to 20 cos 30 degrees. And then you would have a vertical component acting downwards, and that would be equal to F sine theta, or in this case that's equal to 20 sine 30 degrees. Okay, so just keep in mind in terms of what is vertical. Okay, so this is for vertical, and this is for horizontal. We always use cos for horizontal scenarios and use always sine for vertical scenarios. Okay, so again, best to explain this using example. And so we've got this example over here. So we've got a beam going across, like we've seen before. We've got two supports, R1 and R2. We've got diagonal beams, and this is equilibrium triangle, so 60 degrees for those angles over there. Very similar structure as you would maybe have for a house roof, you know. It might be a bit of slant, it's going up at 60 degrees, and these are the supporting beams inside of it. So we've got 2 kilonewtons force acting downwards over there, and 3 kilonewtons force acting downwards over there. These supports points are 10 meters away from each other, so each triangle is 5 meters on a base in terms of dimensions. Okay, so with this type of problem, there's usually two things you've got to calculate. The one is, what is R1 and R2? And then the other thing is, what is the stresses that are experienced, or at least the forces that are experienced in each of these beams that are out over there. Okay, so let's for us to calculate R1 and R2, we're going to be taking this structure and we're going to squash it together into almost a single beam. So we're going to consider this as to being a single beam, and have this height aspect just squashed together. So you'll see when we do the calculations, we're not going to, we've got a force acting of 2 kilonewtons over there. We know it's in the center of this 5 meter piece, so that 2 kilonewtons is 2.5 meters away from R1. And at the same time, we've got the same for the 3 kilonewtons away from R2. So we're just going to squash it together and make as if there's nothing in between over there. Okay, so as we did with the one-dimensional beams, we're going to take moments about R1 for R2. Okay, so remember, anti-clockwise moments is equal to clockwise moments. Okay, so we're going to be looking at R1. We're placing our pen on R1, and we're going to be looking at all the clockwise moments. So that's going to be going around it in a clockwise direction, and that would be this 2 kilonewtons and 3 kilonewtons that would be considered as part of it. Okay, so we've got that 2 kilonewtons over there. Multiply that by a distance of 2.5 meters plus the 3 kilonewtons, and we're going to multiply that by, so if this 3 kilonewtons is in the middle of 2.5, that would be 2.5 plus another 5, that would be 7.5 meters. And that is going to be equal to R2. If we look at the anti-clockwise directions, R2 is 10 meters away, and that's the only force working in anti-clockwise direction, so it's 10 R2. Okay, so when we calculate R2, we are able to get it to equal to 2.75 kilonewtons. Right. Now let's take moments about R2 for R1. Alright, so clockwise moments is equal to anti-clockwise moments. Alright, so again we're going to be looking at R2 as our pivot point, and we're looking at all the clockwise directions. So at the moment R1 is the only force acting in a clockwise direction around R2. So that would be 10, therefore 10 R1s are equal to, and let's look at the anti-clockwise directions. That's again the 3 and a 2. So that would be 3 times 2.5 meters. You'll notice I'm not putting kilonewtons over there because all our forces are in kilonewtons, and my final values I will put the units in as kilonewtons. Okay, plus, and then we've got a 2 meters, and that's also 7.5 meters away. Right, and if we then calculate what R1 is, R1 will be equal to 2.25 kilonewtons. Okay, so now we've calculated, we can actually add these values in here. R1 is equal to 2.25 kilonewtons, and R2 is equal to 2.75 kilonewtons. Okay, so now we've set up the values. We can see everything happening over there. One of the things I'm going to do now is I'm going to make all the beams to be considered as struts. And I know that there are times that are considered as ties, and you'll see we are able to identify whether our ties, if we made a mistake in terms of struts, and they should be ties. Okay, so I'm going to make everything struts. So that's going to mean that all the forces are going to be meeting up, for these beams are going to be meeting up at the different points. Okay, so we add these with like arrows to indicate that it's struts. As such. Okay, now that we've done that, we've got to, what I'm also going to be doing is I'm going to make each point where these beams, whether struts or ties, come together, I'm going to label them. So I'm going to call this A, I'm going to call this B, this will be C, this will be D, and that will be E. Okay, so now I've laid out the problem, I've labeled everything, and I'm going to use that to do my calculations. Okay, now keep in mind that with these systems, with any beams where there are struts and ties involved, it's an equilibrium system. So in other words, at each of these points, the sum of the forces are equal to 0. Okay, so we're going to be using that to do the calculations. Okay, so I'm going to start off with point A. Okay, and what I'm going to do is I'm going to say all upward forces are equal to downward forces. Okay, so therefore the upward forces over there, we know this is 2.25. So 2.25 is equal to, and there's no upward force, other upward forces at that specific point. Downward forces is going to be this beam over here. That's going to be acting downwards, but in a vertical direction. So remember, when we had to look at vertical directions, it's that force multiplied by sine of theta. Okay, so we know these are all 60 degrees. So that would be AB sine of 60 degrees. Okay, so we use that, we make AB the subject of the formula, and we get that AB is equal to 2.598 kilonewtons. Okay, now while I'm at point A, I'm going to be looking at forces going in the right direction and compared to them to the forces going in the left direction. Okay, so and by the way, well, this will be a strut, but we will I'll show you how I know that and how I confirm that in the next continuation of this calculation. Okay, so now I'm going to say forces going to the right hand side is equal to the forces going to the left hand side. Remember, sum of forces are always equal to 0, and that would be always for your vertical and horizontal directions. Okay, so if you look at point A over here, what forces are acting towards the right hand side? There's no forces acting on the right hand side. All of these are acting some other way towards the left. Okay, so therefore 0 is equal to, now let's have a look at all the forces acting towards the left hand side. Okay, so we can see from this that there is going to be AE that's going to be acting to the left hand side. We don't know what that is, so that is AE. And then it's going to be the horizontal component of AB. Okay, so that's going to be plus, and we know AB is equal to 2.598 kilonewtons. Okay, so 2.598 cos 60 degrees. Okay, now we make AE the subject of the formula. So therefore, AE is equal to minus 1.299 kilonewtons. Okay. Now you'll see that we've got a negative sign over there. So what that actually indicates to us is whatever we thought it was, we thought it was a strut. If it's a negative value, it means it must be a tie. Okay, so that means that this is 1.299 kilonewtons, but it is a tie. And because this one was positive and we assumed it was to all the beams to be struts, and this became positive, we can then therefore assume, or we know that this is a strut. Okay. Alright, so now that we've done that, let's have a look at the next point. So that was point A that we looked at. I'm going to be looking at point B. So what I'm going to do is I'm going to just draw a line over here to separate my calculations. Okay, so point B. Okay, so if we look at this diagram, I know I'm going to mark the beams that we've already got values for. We know what this one's value is, we know what that one's value is, we've calculated that. Now we need to find out what the other values are. Okay, so what I'm going to do is I can actually, maybe I've considered E, but over here at E I've got one known and three unknowns, which makes it difficult to calculate. Over here at B I've got two unknowns and I've got one known. Maybe there's a way that I can go about to do a calculation. So let's have a look. Let's say upward forces equal to downward forces. Okay, so looking at upward forces, we can see that there's going to be this AB that's going to act with the vertical component, so it's going to be multiplied by sine 60. Okay, so therefore AB is 2.598 sine of 60 degrees. Okay, we can see over there that there is also this force BE that will be acting upwards over there with its vertical component, so we can add that over there. So plus BE sine of 60 degrees. There's no other upward forces we can see over there. Okay, and that is equal to the 2 kilonewtons acting downwards over there. Okay, so now we can make BE the subject of the formula, and when we do the calculations we can find that BE is equal to negative 0.288 kilonewtons. Okay, so now that it's indicating the negative, that will also indicate to us that it is a tie and not a strut. Okay, now that we've looked at the upwards and downward forces, let's look at the right hand forces and left hand forces. So remember, right hand side forces are going to be equal to the left hand side forces. Okay, so now if we look over there, what forces are acting towards the right? Well, AB is acting towards the right, BE is acting towards the left, and BC is acting towards the left. Okay, so let's have a look. We know that it's therefore AB cos 60 degrees. That's going to be acting to the right hand side. Anything else acting towards the right hand side? Nothing else that we can see over there. Let's see the forces acting out in the left hand direction. Okay, so that's equal to, so that is BC. That beam over there is going to be acting in that direction. And we're going to have plus BE, multiply that by cos 60 degrees. Okay, now remember we've already calculated what BE is, so I can tick off that beam over there. We know what that value is. Okay, so now that we've done that, so AB is equal to 2.598 cos of 60 degrees. That's equal to BC, we don't know, so that's BC over there, plus, and BE we know that is, but now keep in mind it's a negative value over there, so we've got to take that into account. So that is minus 0.288 cos of 60 degrees. So the sign over there is important as well. Okay, so that if we're going to be using these values in other calculations, so even though we know it's a tie, we can make it a positive and then make the arrows coming towards each other. It just makes things complicated and there's chances of making error. So rather keep it as it is and then use those values in the calculations. Okay, so now we make BC the subject of the formula. So therefore, BC is equal to 1.443 kilonewtons. Okay. It's a positive value. So what does that mean? It means it's a strut. Right. Now that we've done that, we can actually tick off another beam. So we know what BC is. So we can tick that one off. Okay. Let's have a look at another point. So I'm going to be looking at point D. That is another easier one. There's less forces going towards it. So let's have a look at point D. Okay, so upward forces is equal to downward forces. Okay, so the upward forces at point D is 2.75. That is for R2. Any other upward forces over there? None that we can see. Okay, what about downward forces at point D? Well, we can see that this CD is going to have some downward force over there. Okay, so we're going to say that is equal to CD, and downward forces is sine theta, so sine of 60 degrees. Alright, so now we can make CD the subject of the formula, and we can say that CD is equal to 3.175 kilonewtons. Again, it's a positive value, so what does that mean? It's a strut. Right. Now we're going to be, while we're at point D, we can say, well, right hand side force is equal to left hand side forces. Okay. So if we look at forces going towards the right, well, ED will go towards the right. So we've got ED. And we've got also this CD value that is going to act some force towards the right. Okay, so we've actually got CD, so we can tick that off. Okay, so looking at that, we can say that it's going to be plus CD, and CD we know is 3.175 cos of 60 degrees. Okay, what forces are acting in the left hand direction? Well, there aren't any forces acting in the left hand direction if we look at this diagram. All the forces are acting towards the right hand side. So therefore that's equal to 0. Alright, so now we make ED the subject of the formula, so therefore ED is equal to, and that's minus 1.5875 kilonewtons. It's a negative value, so that implies it's a tie. Right. Now that we've done that, we've got, essentially, we've calculated all except one beam. So we've got ED, so we can actually tick ED off on the diagram, so we know that we've got that. We still don't have CE, so we need CE or EC. Okay, so for this I'm going to now use point C as a point that I'm going to be focusing on doing my calculations. Okay, so point C. Okay, again, upward forces equal to downward forces. Alright, so upward forces is equal to downward forces. You could probably do the right hand forces equal to left hand forces over there as well. You should get the same answer. I'm just doing upward forces and downward forces because I've already got one known over there that I was given of 3 kilonewtons, so it decreases my chance of maybe calculation error if I did somewhere a calculation error. So for example, if BC was calculated incorrectly over here, I'm not using BC again, I'm using my other forces. There's still a chance that I could have maybe made a calculation error, but I'm trying to minimize it. Okay, so upward forces is equal to downward forces. Okay, so let's have a look. What upward forces do we have over here? Well, we've got EC sine 60. We've also got CD sine 60. Okay, there's no other forces going in the upward direction. What forces are going downwards? Well, it's at 3 kilonewtons. That's the only forces going downwards. Okay, so that's equal to 3. Okay, so now I know that CD is equal to 3.175. Okay, so therefore EC sine 60 degrees plus 3.175 kilonewtons sine of 60 degrees is equal to 3. So now I make EC the subject of the formula, and I can get an answer over there of 0.289 kilonewtons. I could have converted this to newtons, but because everything else is in kilonewtons, I'm trying to keep to the same convention of keeping everything into kilonewtons. Okay, so now we can tick off this beam over here. So now we've calculated all the different forces in each of the different beams. This one over here, obviously we know that that's a positive value, so that implies that it's a strut. And we've also now identified which of these beams are struts or ties. Okay, so we're going to be, essentially, it doesn't matter what problem you're having, the same procedure will happen. You'll basically look at the upward forces, downward forces of each point, and if possible also look at the left hand forces and the right hand forces to find the unknowns of the forces in the beam structure that you'll be looking at. Let's look at another example. Okay, so this is a little bit more of a challenging problem, but we'll see how to go about to solve it. Okay, so we've got this structure, we've got a beam going across, it's 15 meters away. We told that that's 30 degrees and that's 30 degrees over there. We've got another beam structure coming up over here, that's at 90 degrees. And then we also told that that's 15 meters away. We've got a force of 30 newtons or 30 kilonewtons over there. We've also got a force of 60 kilonewtons over there. And R1 and R2 are our supports that we don't know what those values are. Okay, so first thing we're going to do is we're going to determine what R1 and R2 is. Okay, so take moments about R1 for R2. Right. So what we're going to do is we're going to take it about R1. Okay, so remember clockwise moments is equal to anti-clockwise moments. Okay, so we're squashing this whole diagram together down into a single beam type of scenario. Okay, so we've got the 60 kilonewtons acting downwards. Okay, so therefore it's 60 kilonewtons. And what's the distance of the 60 kilonewtons? In the middle of this 15, because both sides are equal angles, so that means that that is 7.5 meters away. Okay, multiply by 7.5 meters. Right, then we've got this 30 kilonewtons acting downwards, so we're going to add over there the 30, and we're multiplying that by, okay, now what distance do we multiply this by? Okay, so now it becomes a bit of a situation where we need to do an additional calculation. Okay, so what I'm going to do is I'm going to extend this bottom beam with this line just with the dotted line as such, and then therefore where this 30 kilonewton force is coming down, I'm going to have a dotted line coming down over there. And we know that this is 90 degrees. Okay, so if we have a look at this, if this is 90 degrees, and that is 30 degrees over there, and we've got 90 degrees over there, that means that this must be then 60 degrees. Okay, so we can indicate over there that's 60 degrees. Now we know the formula of x is equal to r cos theta. So we needing to get this x over here, we know what r is, that is this 15, and we need to identify what this x value is. Okay, so that's equal to 15 multiplied by cos of 60 degrees. And you do that calculation, you find that x is equal to 7.5 meters. Okay, so now that we've got that distance, we can then use that to this calculation. So that we multiply that by, now it will be 7, if this is 7.5 meters, it's going to be added to this 15 meters over here. Okay, so that means that this is 22.5 meters. Okay, now let's look at the anti-clockwise directions, because there's no more clockwise direction forces that we can see. So anti-clockwise directions is the R2. Now R2 is 15 meters away, so that is equal to 15 R2. Alright, so now that we've got this, we can make R2 the subject of the formula, okay, and we will calculate that R2 is equal to 75 kilonewtons. Okay, right, so now we're going to take moments about R2 for R1. Okay, so remember, clockwise moments is equal to anti-clockwise moments. Right, so therefore, we've got now R2, that's our pivot point. So clockwise moments, that will be R2, that will be going in the clockwise direction over there. I say R1, that's going to go clockwise direction over there, and that's 15 meters away. So 15 R1s. Is there anything else going in the clockwise direction? Well, the 60 is not going in the clockwise direction, it's going in the anti-clockwise direction. But if you look, the 30 kilonewton force is acting in the clockwise direction. Okay, so plus 30 multiplied by, and it's away 7.5 meters. Remember, we calculated that over here. Okay, so multiplied by 7.5 kilonewtons. Okay, there's no other forces we can see acting in the clockwise direction. Now let's look at those acting in the anti-clockwise direction. Well, there's only the 60 over there, the 60 kilonewtons, so that's equal to 60, and the distance that 60 kilonewtons force is from this R2 is 7.5 meters. Okay, so we can calculate R1, make it a substitute of the formula, and we are able to identify that that is equal to 15 kilonewtons. Alright, so now that we've done that, we can actually add these values over here. So R1 is equal to 15 kilonewtons, R2 is equal to 75 kilonewtons. Okay, so now we've got all our forces set up over there. Okay, so what I'm going to do now is I'm going to again label all the points. I'm going to assume all these intersections, or all these intersections of these beams are struts. So all the arrows are going to be pointing towards each other as such. Now I'm going to label what the different points are. Okay, so I'm going to say that this is A, I'm going to say that this is B, this is C, then this will be D. Right, and that's it. Okay, so I'm going to start off with looking at point A. Okay, so upward forces is equal to downward forces. Okay, so if we look at point A, upward force is going to be R1. Okay, so we can say, therefore, R1 is 15. Is any other forces acting upwards? No, we can't see any more other going upwards. Okay, and that's equal to, what's the downward force? Well, that will be AB sine of 30 degrees. Okay, which is equal to, if we therefore make AB the subject of the formula, we will find that AB is equal to 30 kilonewtons. It's a positive value, so therefore it's considered to be a strut. You need to indicate if it's a strut or a tie. Okay, now that we're still at point A, let's look at forces going to the right hand direction must be equal to the forces going to the left hand direction. Okay, so forces acting in the right hand direction over there, well, there's none over there that's going in the right hand direction, so that's equal to, therefore we can say that that is 0. Okay, so 0 is equal to forces acting in the left hand direction. Well, it will be, as we can see over here, it's going to be AD. Okay, and then we've got also this force AB that's going to have a horizontal component. Okay, so plus AB cos 60 degrees, 30 degrees. Okay, we know what AB is. AB is 30 kilonewtons, so that's equal to AD plus 30 cos 30 degrees. Make AD the subject of the formula, and we calculate AD is equal to negative 25.98 kilonewtons. It's a negative value, so therefore it implies that it's a tie. So now that we've done that, takes care of point A. We're able to do now calculations for any of the other points over there. Well, if you have a look at all these points over here, it becomes a little bit difficult now. Okay, so let's just mark which beams we've now calculated at least the forces in them. So we've got AB, so we know what that one is. We know what AD is, so that's AD over there. Okay, if we have to calculate, look at let's say point B, we've got the upward force. If we look at upward forces and downward forces, we've got the upward force of AB, we've got, which we know, we've got the upward force over there of BD, which we know, but we've also got this downward force over here of BC, which we don't know. Okay, so there's two unknowns that we don't know. Okay, if we have a look at point D, we've got one known over there, but again we've got two unknowns over there, which makes it a bit difficult, and they've both got horizontal and vertical components. And the same thing with point C. It's got both of those beams have got horizontal and vertical components. If you have a look at point A, for example, you'll see that we've got a vertical component, which was R1, and we've got a vertical component of beam AB, but beam AD that doesn't have a vertical component, so that was possible for us to calculate. Because this becomes now a little bit tricky. Okay, so what we're going to have to do is we're going to have to do simultaneous equations. Okay, so we're looking at point B. Okay, so I'm going to say again, upward forces is equal to downward forces. Okay, so if we have a look at point B, what upward forces are we going to have? Well, we're going to have AB sine of 30 degrees. Okay, so that AB we know is 30 kilonewtons, so therefore 30 sine 30 degrees. we've got the upward force over there of BD, going also sine up of 30 degrees. Okay, so plus BD sine of 30 degrees. Okay, so we've taken into account that force going upwards over there. We've taken into account this force going upwards over there. Okay, is any other forces going upwards over there? No, none that we can see. Okay, so now we're looking at downward forces. Well, we've got the 60 kilonewtons over there that's going downwards. Okay, so that is going to be 60 over there. And then we've also got BC acting in a downward, at least with a vertical component. Okay, so plus BC, that's going to be off. Now keep in mind, we're not looking at this angle over here. We've got to look at the horizontal components with the horizontal plane. So that would be our x-axis over here and our y-axis that we're always considering. So that means there's 30 degrees to be taken into account over there. Okay, so BC, and that's going to be sine of 30 degrees. Okay, now that we've got that, let's have a look at the forces going towards the right and forces going towards the left. Okay, so right hand forces must be equal to left hand forces. Okay, so if we look at point B again, what forces are acting in right hand direction? Well, AB is going to have a horizontal component acting over there. Okay, so we know that AB is equal to 30. Okay, and that's going to be cos 30 degrees. Okay. Now, there's no other forces acting to the right hand direction, so that's equal to, now so let's look at all the forces going in the left hand direction. Well, that's going to be BD cos of 30 degrees. And we've also got BC that is going to be acting in, towards the left. So plus BC cos of 30 degrees. Okay, so now we've got essentially two equations. I can call this equation 1 and that equation 2. And now we have to solve simultaneous equations. Okay, so we're going to put 2 into 1. Okay, so that's what we want to achieve. Alright, so if we have a look at this, we're going to be placing this equation into the equation number 1 over there. Okay, so for me to be able to do that, I need to make one of these unknowns the subject of the formula. So I'm going to say for this equation over here, for equation 2, that BC is equal to 30 cos 30 degrees minus BD cos 30 degrees, and we're going to divide that all by cos of 30 degrees. Okay, so substituting now this BC into equation 1, we get that therefore 30 sine 30 degrees is equal to BD cos of 30 degrees plus BD sine of 30 degrees. I'm looking at the wrong equation. It's BD sine of 30 degrees. Okay, and this needs to be a plus, not the equals. Okay, so again, just look at it, 30 sine of 30 degrees plus BD sine of 30 degrees. Okay, and that is going to be equal to 60 plus BC. Now BC, we know what's this over here. Okay, so that is going to be 30 cos 30 degrees minus BD cos 30 degrees divided by cos of 30 degrees. and that is all going to be multiplied by sine of 30 degrees. Okay, if you have a look at the substitution that we've just made over here, you'll see that we've got cos 30 degrees in both terms in the top, and we've got it in the denominator, so they can actually cancel out with each other. Okay, and that will simplify our equations quite drastically. Okay, so therefore 30 sine of 30 degrees plus BD sine of 30 degrees is equal to 60 plus, and that's going to be 30 minus BD and that's all multiplied by sine of 30 degrees. Okay, so over here we are able to say this is the same as saying 30 sine 30 degrees minus BD sine 30 degrees. Okay, so now what we're going to be doing is we're going to now therefore go and make BD the subject of the formula. Okay, and when you do that, you'll find that BD is equal to 60 kilonewtons. Okay, again, it's a positive value, so what does that indicate to us? That is a strut. Okay, now we've got to we've got BD, and we've substituted 2 into 1, so now we've got to take this BD and substitute into 2, so that we can calculate then what is BC. Okay, so therefore 30 cos 30 degrees is equal to BD cos 30 degrees plus BC cos 30 degrees. Okay, and we know that BD is 60 kilonewtons. Okay, so therefore 30 cos 30 degrees is equal to 60 cos 30 degrees plus BC cos 30 degrees. Okay, so BC we make the subject of the formula, and therefore we calculate BC is equal to minus 30 kilonewtons. Okay, and that will imply that it's therefore a tie. Okay, so that was a little bit of a challenge to do, but it was plausible. Okay, now that we've done that, we can just draw a line over here. I've got a little bit of space over here at the bottom, just to separate my calculations. So now, let's have a look. We've got BD. We've calculated that, so we can tick that off. We've calculated what BC is, so we can tick that off. The only unknown that we've got now is CD. We need to calculate what CD is. Okay, so for CD, I'm going to use point D as my point that I'm going to be doing a calculation set. Alright, so again, I'm going to say upward forces is equal to downward forces. Okay, so upward forces at point D is 75. Are there any other upward forces at point D? None that we can see over there. Okay, let's look at the downward forces. Okay, well, we've got BD that's going to be acting downwards to some degree. Okay, so that is BD sine of 30 degrees. And then we're also going to have CD acting downwards over there. So plus CD sine of 30 degrees. Is it 30 degrees? Okay, so we've got CD acting down that way. We've got 60 degrees over there that we need to use, not 30 degrees. Okay, so just be careful with the angles that you are using. Okay, so now we make CD the subject of the formula. So therefore CD is equal to 51.5 25.962 kilonewtons. So positive values, that implies it's a strut. Alright, so now to finalize everything, we've calculated everything. We can actually then go and tick off this one over there as well. We found the forces in all the beams in the specific problem. What I'm going to now do is I'm going to just lay out all the values that we've just calculated, so that you don't have to try and figure out where they are over here, and then also be able to indicate if they're struts or ties. Okay, so a beam is equal to 30 kilonewtons, and it's a strut. Okay, then I'm going to say, okay, the next one we've got is AD. That is equal to 25.98 kilonewtons, and that is a tie. Then we've got CD. CD is equal to 51.962 kilonewtons, and it's a strut. Then we've got BD. BD is equal to 60 kilonewtons, and it's a strut. And then we've got BC, which is equal to 30 kilonewtons, and it is a tie. Okay, so now it just summarizes everything of all the forces that we've calculated, so that you don't have to look for it in all the calculations over there. Okay, so you can actually say this is your final answer. Okay, so as you can see, we essentially went and again took the problem, we went and squashed it together into a single beam type of scenario that we were familiar with. We calculated what R1 and R2 was. Then we looked at each point, considered all the beams to be struts, and we looked at upward forces equal to downward forces and right hand forces equal to left hand forces. Did the calculations. We did come to a point where we had then two unknowns that we had to then calculate, so we used simultaneous equations. It wasn't difficult, but just was a little bit more extra work we had to do compared to the normal calculations. And then after we've done that, we were able to then calculate the only last unknown that we didn't know over there, and then we were able to place our final calculations and answers over there. So the same type of scenario is going to happen for all the type of problems that you come across, and it's important just to make sure that whenever you start these problems, look at what is the least unknowns that you've got at each point. If you've got more than let's say two unknowns or more, it might be better to go and look for a point that there's less unknowns. And like we started off with point A, where there was, if we looked at upward forces and downward forces, there was only one unknown that we had to do. So the same type of procedures will have to be followed, and that will be used for all these type of problems that you come across. This is a remote pilot aircraft system, or RPAS. It's a fixed wing. It's got 1.8 meters wingspan, and it's one of the common fixed wing RPAS or drones or unmanned aerial vehicles that could be used by people. But before we go into seeing how the moments can be used and how they are useful and stuff, let's just have a look at some of the platform or vehicle dynamics in terms of how it moves around. Okay, so the first thing we need to look at is pitch. Pitch is the motion of the nose of the aeroplane going upwards and downwards. Okay, and note that pitch is controlled by the elevators, which you see on the tail. So moving upwards and downwards. And then we have got yaw, which is a motion towards the left and towards the right. Okay, and yaw is controlled by the tail, with the rudder. And the rudder will move to the left and right, and that will change the yaw of the airplane. And then we've got what's known as roll, and roll is a motion towards the left and towards the right. And the roll motion is performed by the ailerons, which are on the main wing, and they're able to move upwards and downwards. Okay, so now that we've got the three basic motions in place, let's just see how it works. So with the ailerons, when a roll has to happen, the one aileron will move upwards, the other aileron will move downwards. Okay, so in this case, if this aileron had to move upwards, and this one had to move downwards, what's going to happen is the wind's going to hit against this aileron, and using Newton's third law, is going to essentially push down this wing, yet the wind will be coming, or the airflow will be coming at the bottom of the wing. It will hit this aileron at the bottom because it's facing downwards, and that will cause this wing to push upwards. Okay, so that is how your roll motion is able to happen. Your motion happens with the tail. So how this rudder works is that, let's say it moves towards you, then the air is going to flow, it's going to hit this rudder, and it's going to push the back towards the left, which is going to cause the airplane to yaw towards the right. So the tail or the rudder is able to control the yaw motion of the airplane. The same thing is if you had to move the rudder to the opposite direction, it will cause the wind to come past, it will hit against the rudder that is facing towards me, it will push the tail towards the right, which will cause the nose to go towards the left, and so it will yaw towards the left. And then finally, you've got the elevators that are at the back, and they often operate in a very similar fashion. So what would happen if they were moved or in an upwards position like that? The airflow would come past, it will hit those elevators, and it will, because they're lifting up a little bit, it will cause the tail to go downwards. And as the tail goes downwards, it means that the nose will be pushing upwards. And again, vice versa. If the elevators were pointing downwards, the airflow will come underneath the wing, it will hit those rudders, those elevator control surfaces, it will push the tail upwards, and therefore the nose will pitch downwards. Okay, so the center of gravity of such an aircraft is important, and it's generally that it is designed to have a center of gravity at least at the center of the wings. And as a matter of fact, if I take my fingers and I hold here in the center of the wings and I lift up, you will see that the aircraft is balanced. So it won't be tipping forwards or backwards, it is balanced underneath the wings. And so you generally want to have the payload, or most of the weight, as much to the front as possible. The reason being is that if you've got a control surface like your elevator that's got to move upwards and downwards, if the center of gravity was towards the back, because of the arm length being so short then, and therefore also the moment being so short, will cause that the amount of force the pilot has to put on the control stick to move these elevators up and down will be a lot, and will be very difficult to make the aircraft to pitch upwards and downwards. Yet if you can have the weight towards the front of the aircraft, like you'll often find the engines are in the front of the aircraft, a lot of the luggage or people might be sitting towards the front of the aircraft, then that will cause it to have a longer arm length, and therefore there will be a larger moment. So there's less input that the pilot would have to give to control these surfaces. Right, so as a manned aircraft pilot, as well as a remote pilot and also a remote pilot or RPAS instructor, with those ratings we often have to do these weight and balances on small aircraft such as this, as well as a manned aircraft. And if any of those calculations for the mass and balance should be a little bit out of a certain window, then we've actually won't be able to fly. You might be able to take off, but there might be problems when you want to land. Or you might not be able to take off because the weight distribution within the aircraft could be incorrect. So weight and balance is very important for pilots, and they've got the responsibility of the aircraft and of the flight and of the passengers on board. And so, for safety reasons, they've got to make sure that all the things are inspected around the aircraft, as well as making sure that the weight and balance of the aircraft is satisfactory for safe flight. Another application of a vehicle that will also be yawing, pitching and rolling is the minibus. And over here we made it remote controlled, and we tried to see if we could roll it over. The center of gravity on these type of vehicles are very low, able to tip as if the center of gravity is higher. So if we had more passengers in the vehicle, it would become more unsafe. The Sling 2 aircraft is a two-man aircraft, and due to the size of it, is weight and balance very important, because a little bit of uneven balance in the aircraft or something that might be able to move could cause major control issues. Let's have a look at the mass and balance of the Sling 2 aircraft. So this is a typical form that the pilot would have to complete. Okay, so the formulas are essentially shown over here that would for completing different fields. Okay, so initially the pilot would have to indicate how many liters are available in the aircraft. So in other words, this will be in liters. The maximum is usually for the Sling 2 at least is 150 liters, and then the that value would then be taken and multiplied by 0.72 to be able to get the actual weight of your fuel. Keep in mind that fuel has a density that is less than water, and so it will be therefore a value that would be less than 1 for the density, so therefore it's 0.72 has got to be multiplied with. Okay, so the aircraft has a known empty weight of 397.4 kilograms, and then you've got the option to be able to say what the right seat person's weight is, the left seat person's weight is, the baggage in the front and the baggage in the rear. So these weights can be then placed in over there. It's important to also keep in mind that there are mass limits. So for example, the front baggage can't be more than 35 kgs and the rear baggage can't be more than 25 kgs. Same time, the fuel cannot be more than 8 kgs. So even though we've got a maximum weight of or maximum amount of 150 liters of fuel that can go into the aircraft, there is a limit in terms of how much weight that fuel can occupy. And then we've got a takeoff mass. It's also got a limit of 700 kgs over there. Okay, so your takeoff mass is in essentially adding up all these weights together, and you've got to always also include the empty value over there of 397.4 to get that sum over there. And then the moments have to be calculated. So this specific weight or force that we've got over here is multiplied by the arm length to get the moment. Okay, so for example, 397.4 multiplied by 1671 is equal to 664216. And so each weight over here is multiplied by the arm length to get your moment. And that's done for all of them over here. Finally, once you've done it for all of them, you're able to add all these moments together to get the sum of the moments over there. And then the arm can be calculated by taking this moment value and dividing it by the total mass to get your total arm length over there. Okay, so then there's your percentage Mach empty that has to be calculated. So percentage Mach stands for mean aerodynamic chord. Okay, so the percentage Mach when it's empty is calculated. So essentially this is taking the sum of the moments, but all of those with the stars next to it. So if your fuel tank is going to be empty, obviously you're not going to have any fuel over there, so this value over here will be 0. Okay, so you're basically going to add all of these moment values together. Remember to also include the moment value calculated there for the empty aircraft. You're going to divide it by the sum of the weight, which is the sum of the weight of that you've entered in over here in this column. But keep in mind fuel is 0, so therefore we won't be adding up the fuel value over there. Minus 1366, and then all of that in brackets multiplied by 100 and divided by 1339. Okay, and then the mass of it being empty is, again, we're just adding up all these values except for the values of the fuel, and we'll place the value over there. The percentage Mach, and again Mach is mean aerodynamic chord, so the percentage Mach at takeoff is going to be your takeoff arm, which will be this value over here that we've calculated, minus 1366, and then we're going to take that answer, multiply it by 100 and divide by 1339. Again, the mass takeoff is going to be essentially all these weights that we've calculated over here, and it's going to be the takeoff mass over there that we've already calculated, which will be entered in over there. And then once we've done that, then we can plot this percentage Mach empty and the mass empty as XY coordinates on this specific graph. And we're also able to then look at the percentage Mach at takeoff and the mass at takeoff and plot in this specific graph. And we've got to make sure that the empty and takeoff percentage Mach is within this envelope or within this specific rectangular shape, and if it is, it's safe then to take off or land. If it's not, then it will be unsafe, and then we've got to relook at getting lighter passengers, maybe decreasing the luggage, maybe decreasing the fuel even. So it all depends on what it is, and then we have to adapt the masses in the aircraft to be able to accommodate it so that these values will be plotted within this rectangular space. It's better to show it by using an example. Okay, so here we've got a clear mass and balance sheet, and we're going to complete it. So in this specific example, we're going to assume that we've got 50 liters of fuel. So we'll place 50 over there. And 50 multiplied by 0.72 is going to give us the mass of the fuel, which will be then equal to 36. Okay, now let's say in the right hand seat you're told that there's a person sitting over there of 110 kgs, and on the left hand seat there's a person sitting over there that's weighing 100 kgs. You're told that in the front baggage or luggage it's got a total weight of 10 kgs, and then we've got the rear baggage which has got a total weight of 25 kgs. Okay, so up to this point these values are correlating over here with the mass limits. It is within those limits, so we know it's safe to look at least to use them. Okay, so we can add up all these values together, and adding up all these values together we get a total of 678.4 kgs. Okay, now that we've done that, we're going to multiply each of these weights with its correlating arm value to get the moment. So 110 multiplied by 1959 is equal to 215,490. 100 multiplied by 1959 is equal to 195900. 10 multiplied by 2508 is equal to 25080. Then we've got the rear luggage, which is 25, multiply that by 2896, and we get 72400. And then we're going to say 36 multiplied by 1511, and we're going to be getting a value of 54396. Okay, now that we've done that, we're going to add all of these values together. So 664216 plus 215490 plus this value, that value, that value, and that value. Adding them all together, we're going to get a value of 1227482. Okay. Now we're going to take this value that we've just calculated and we're going to divide it by 678.4, and that will give us our arm length. So that is equal to 1809.3779. Okay. Common mistake is that people think that they need to add all these arm lengths together to get this value, but it's not. It's this moment over here, divide by the takeoff mass, and you get this arm value over there. Okay, now that we've done that, now we need to calculate the percentage Mach when it's empty. So we're going to be taking the sum of these values over here with the asterisks next to them. We're going to divide them by the sum of the weight over here. So remember, the empty value of the aircraft weight we're going to take into account as well, except for the fuel weight over here. So we can't go and take this final takeoff mass value, it won't work. So it's going to be 397.4 plus 110 plus 100 plus 10 plus 25. Okay, and then once we've calculated that, we're going to subtract 1366 and get an answer, multiplied by 100 and divide by 1339, and we will get an answer of 34.36. And then we'll also be looking at what is the mass when it's empty. So remember, that is going to be all the values over here except for the weight of the fuel. So 397.4 plus 110 plus 100 plus 10 plus 25, and that's going to give us an answer of 642.4. Okay, now that we've done that, let's look at what the percentage Mach for takeoff is. Okay, so essentially we're going to take the takeoff arm, which we've calculated over here as 1809.3779. We're going to subtract 1366. We're going to get the answer for that, multiplied by 100 and divide by 1339, and we will get an answer of 33.11. Okay, and then what's the mass at takeoff? Well, that is this already calculated over there in this field. It's 678.4 because we've taken into account all the weights over here, adding up together, so we can place that value over there. That's 678.4. Okay, so that's the same as our takeoff mass that we've calculated over there already. Okay, now that we've got these values, we've got to now plot it. Okay, so first we're going to be looking at for empty. So percentage Mach at empty is 34.36. Okay, so if we look at our graph over here, 34 is located over there, 0.36, so it's going to be a little bit over that. Okay, so we know it's going to be over here somewhere, and if you can see the faint line over there, it will be just to the right of that faint line. The mass at empty is 642.4. So if we look at the aircraft mass over here, it's 642.4. So that's going to be very close to 650 over there. So it's just going to be below 650. So we can bring that across over there. So we can make a mark over there. That's going to be our percentage Mach empty. Okay. Then we're going to be looking at the percentage Mach at takeoff. Okay, so we've got 33.11. Okay, so 33 is between 32 and 34 over there. So it's just past that, so it's going to be somewhere located over here. And we've got a mass takeoff of 678.4. Okay, so 678.4. So that's going to be between 650 and 700 over there. Okay, and so for that we're going to find it will be located roughly over there. Okay, so that's going to be our percentage Mach takeoff. Okay, so now we've plotted both of those points that we've got over here using those values for our X and Y's axes respectively. Now, is it safe to take off with this aircraft? And the answer would be no, because both the percentage Mach at empty is outside of this envelope or this rectangular box, and our percentage Mach at takeoff is outside of this rectangular box. So for both cases, for takeoff and for landing, with landing you're going to be assuming that you might have a complete empty fuel tank. It will be unsafe to perform with this specific configuration. So it won't be safe, and therefore if a person would want to still fly with this aircraft, they would have to reconsider, relooking at the values of the luggage, maybe get lighter people to sit in the seats over there, maybe use less fuel over there, and they would have to play around with these numbers until they get both of these points within this rectangular shape. And if once that's happened, then they can sort of say, okay, now they can take off and have a safe flight.